Okay, I've got the recording turned on now. We have been talking about hybridization and how hybridization impacts the bond angle of different carbon species. I need to draw a chart, a table for you. I typically don't do this, but I think this is one area where having a table can be helpful. You'll see why I don't draw tables as soon as I do this, because I'm terrible at it. This is the bottom of 1.9. I didn't have time to get here on Friday. So let's compare a molecule. And this is in your book. If you don't want to copy down a table, this is in your book as well. But we're going to compare its bond strength and bond length. So let's compare ethane, which is a single bond between two carbons. What's the hybridization of each one of those carbons? sp3. They each have 4 bonds. That's how you know they're sp3. To ethene, it looks like this. What's the hybridization of each of those carbons? sp2. There are 3 bonding domains here, or 3 electron domains. 1, 2, 3. So sp2 hybridized. To ethyne, which are sp hybridized, right? There's 2 electron domains on each side of those. Which of these molecules, ethane, ethene, or ethyne, has the strongest CC bond? Which one of these is hardest to break apart? Ethyne, because there's a lot more electrons holding them together. Ethane is easiest to break apart. Kind of. Let's get into the details here a little bit more. So if I want to look at breaking apart the carbon-carbon bond, for ethane, it is 377 kilojoules per mole. Okay, so don't worry so much about the number here. We'll use the numbers in a second. Kilojoules is the amount of energy. Moles is the amount of stuff. So if I wanted to break apart a group of ethanes, I would have to pour in 377 energy units to make that happen. Do we think that the bond energy, the bond length, I'll just bring that up here, is 154 picometers. So picometer is a small fraction of a meter. On the bond strength, when I go from ethane to ethene, we said we thought the bond was going to get stronger. Okay? Probably what? What would we estimate ethene to be? A little bit stronger, twice as strong? What do you think? Twice as strong, right? It's kind of a logical way of approaching it. Ethane has 1 bond between the 2 carbons. Ethene has 2. So if you take 377 times 2, you would expect this to be 754. Some of you can do that in your head. I definitely did this before class on a calculator. To each their own. You would expect 754 kilojoules per mole, but when you actually measure the bond strength here, it's only 728 kilojoules per mole. Well, you may notice that 728 is less than 754. What does that tell you about the double bond of ethene? Not as good. Remember what a double bond is made up of. You just told me about this on the quiz. Carbon here, carbon here. Overlap directly between the 2. What kind of bond is that? Sigma. Sigma bonds are very strong because the electrons are right where they want to be. To make that second bond, I put a p orbital next to another p orbital. What kind of bond is that? Pi bond. Pi bonds are not as strong as sigma bonds. It's not, a double bond isn't this. It's not just 2 sigma bonds on top of each other. It is a sigma bond and a pi bond. And a pi bond is not as good because the electrons are above or below, not right where they want to be. When I go from, so the difference here is 350, from here to here, I added 351 kilojoules per mole. So you would expect if I go to a triple bond, remember a triple bond is 1 sigma and 2 pi's. So I could expect that 728 plus the difference between these numbers would be 1,079. And I'm limited for space here, but again, I got that number by taking 728 and adding the difference between these two numbers. I came up with the idea of, okay, a pi bond is worth 351 kilojoules, because that's what I added here. Well, if I add another pi bond down here, it should just be that number plus 351 kilojoules to get here. But it's not. When you actually take the bond energy, it is 965 kilojoules per mole. So what the heck? A triple bond is stronger than a single bond, but why is it not nearly? This is a big difference, right? Why is it not nearly as strong as what I think it should be? This comes from something called electron repulsion. Electrons want to be near nuclei. Electrons do not want to be near each other. So they want to spread out as much as possible. I got a carbon here and a carbon here. I put a sigma bond between them. I put a pi bond here. I put a pi bond there. There's a lot of electron density now between these two carbon atoms. And what's happening is every time I add another interaction in here, that area is getting more and more and more crowded. Just about every Sunday, I take my son to the gathering place. It is our little piece of paradise. If you've not been there, you should go. It's wonderful. Here's the deal. If someone's shaking, I see a couple people going, yeah, and a couple people going, no. If you're shaking your head no, you're going there at the wrong time. I go Sunday mornings, like really early, nobody's there. We have the whole park to ourselves. We are electrons in our nucleus. It is fantastic. If I sleep in a little bit and we go at like noon, it's hot and it's crowded. And suddenly I'm like, oh, what's going on with my park? There's people everywhere, right? Electron repulsion. We like to have some space to spread out a little bit. Electrons want the same thing. So as I go from a sigma bond to a pi to 2 pi, the interaction becomes weaker and weaker and weaker. So here's the rub. A sigma ethane is weaker than ethyne, but ethyne is more reactive because it contains these very reactive high energy pi bonds that are easy to break. So if I took a machete and tried to just cut the triple bond in half, it would take me 965 kilojoules per mole, a lot of energy. But I don't have to do that. All I got to do is break one pi bond at a time. So I can react ethyne to turn it into ethene and ethene to turn it into ethane. Getting to that last carbon-carbon sigma bond, though, is challenging. So these make for really nasty multiple choice questions about which bond is stronger, ethyne or ethane. Ethyne has a stronger bond. Which one of these molecules contains a more reactive bond? Ethyne does. The MCAT loves to ask questions about this because they get to play on words of there are weak bonds within this triple bond interaction. It's not just 3 sigma bonds sitting on top of each other, right? It's a sigma bond, pi, and pi. So there is structure to this bond. Does that make sense? Yeah. Ethane has a less reactive bond than ethyne. If I cut ethyne, if I wanted to separate the 2 carbons away from each other, it takes more energy to break all of these bonds at the same time than this one. Right. So if it was like a, I don't know, this gives me kind of like a karate thing. You see people where they like stack up bricks and they break them with their hands. I don't know why people are doing that, but if I had to go up and just go hiya and break that triple bond in half, it would take a whole lot more energy than breaking the sigma bond of ethane. But what I could do is go and break one brick here much easier than one brick down here. I can break the pi component of this much easier than I can break the sigma bond up here. As these electrons get stacked more and more between the 2 carbons, the bonds are going to get shorter. And a general principle in chemistry is shorter bonds are stronger. So I go from 154 picometers to 134 picometers, shorter, stronger, to 120 picometers, shorter, stronger. As we move down this list, we have increased bond strength. And increased has an N in it, doesn't it? Increased. And we have decreased bond length. but pi bonds are more reactive than sigma bonds. This is why most plastics contain carbon-carbon sigma bonds. Most plastics don't break down because it's really hard to break this bond. If plastics were made up of a whole bunch of triple and double bonds, they're a lot easier to break down because I can do chemistry to these molecules. It's very hard to do chemistry to sigma bonds. They're just too stable. There's not a lot of reactions that occur there. We'll talk more about that much later on in class. Questions about single, double, triple bonds? Okay. We've been talking about hybridization of carbon. We can also talk about hybridization of other atoms, and other atoms have lone pairs. So if I have things like nitrogen, and oxygen, I need to put some lone pairs to give each one of these structures an octet. How many lone pairs does the nitrogen need to have?
One.
Just one lone pair, because then I would have 2, 4, 6. A lone pair gives me 8. How many electron domains around this nitrogen? How many electron domains? How many places are there electrons around this nitrogen? 4. Very good. We're going to count the lone pair as an electron domain. So I have 1, 2, 3, 4, which means my nitrogen is what hybridization? sp3. I forget if I brought this up in class on Friday or not. So remember, a trick to this is you can use the sp3, sp2, sp with electron domains. You put an imaginary 1 above that s. We don't draw that, but 1 plus 3 is 4. If you count to 4 electron domains, it's sp3 hybridized. If you have sp2, you put an imaginary 1 there, it'd be 3 domains. That's an example of a carbon that has 3 domains. 1, 2, 3. sp, you put imaginary 1s there. That carbon has 1 domain here, 1 domain there, so it has 2 electron domains or is sp hybridized. That's a shortcut way of figuring out hybridization for different molecules. How many areas of electron density are there? And then add that up for whatever's in your sp formula. Oops. How many lone pairs need to go on this oxygen? 2. How many electron domains around this oxygen? 4. 1, 2, 3, 4. Hybridization of that oxygen. sp3. I very quickly drew this over here, so let me do one more. Hybridization of that carbon. sp3. Hybridization of that carbon. sp2. Hybridization of that oxygen. sp2. So the reason is we got 1, 2, 3 electron domains, so sp2 hybridized. Hybridization of this carbon. sp3. Everybody see how I'm doing that? Moving kind of quick here. Counting up the total number of electron domains, it's either going to be bonds or lone pairs, and using that to determine my hybridization. Yep. You count a double bond as 1 electron domain. It's more, so this is more of just a shortcut of how we can get to that. The real answer is this is sp2 hybridized because it has a pi bond. So it has to have a p orbital to make that pi bond. The reason we count it as one electron domain is, that's a shortcut way for us to say, I don't want to have to think about all the orbitals that are around this to get there. Let's try one more. Can I clear this screen? Yep. Yep. That one? Both. What I recommend is when something's drawn like this, I would annotate it and say, I'm going to draw every one of those hydrogens in. How many electron domains are on that carbon? 4. sp3 hybridized. It's just harder to see when it's written like this. I like to work in pictures. So anytime you see a molecule, your book is terrible about this. They would probably write this molecule like this. Drives me crazy. Ugh. No. That's all that says to me. That's not a molecule. Translate that to a calculate structure ASAP. We used to draw molecules like this because there weren't computers. We had to like teletype it and someone was like, and it had to get it across that way. We should not draw molecules like this anymore. Draw them out. Let's try one more. Occasionally, I don't think I've done this in class yet, but occasionally I will give you a try this in class. I'm going to give you a problem and I'm going to shut up for like 30 seconds to a minute. That is not a time for you to go, oh, he stopped talking. Thank God. It is a time for you to try a problem, right? So play along with me here. I'm going to intentionally draw this without geometry here. Fill in the lone pairs if they're present in this molecule. And tell me the hybridization of all non-hydrogen atoms. Any lone pairs in this molecule? A few. Remind me of your name. Chris? Great. Yeah, sorry. Where are my lone pairs? On the oxygens, how many on this one? 2. And on this one? Also 2. How'd you know that? He asked accusingly. Trying to give everybody an octet, right? So that oxygen only had 2 4 electrons, so I had to give 2 more electrons up here, 2 more pairs to get to a full octet there. Everybody get these lone pairs? You need lone pairs on there if you're going to identify hybridization. What's the hybridization of that oxygen? sp2. Very good. What's the hybridization of that oxygen? sp3. Excellent. That carbon? sp2. That carbon? sp3. Man, that would make such a good quiz question. I could just think how easy that would be. I could just like put a molecule on there and I could put arrows and be like, fill in these arrows for hybridization. I mean, I don't teach this class, but if I did, that'd totally be a type of question I would use. It'd be so perfect for grading on quiz 2. Let's talk about another way that molecules can form. So we've discussed valence bond theory and we've discussed hybridization. We're basically trying to make sense of molecules that we can see. There is a more advanced theory that I need you to know about that's pretty crazy called molecular orbital theory. Molecular orbital has way too many letters in it, so we call it MO. Actually, we just say MO. Nobody says MO. Someone's going to leave here and be like, Dr. Green told me about Mo. And someone's going to say, what are you talking about? That dude's weird. Molecular orbital theory describes electrons around an entire molecule, not just individual atoms. Well, I'll leave the not just around. So we have been talking about hybridization, right? A carbon is sp3 hybridized. A carbon is sp2 hybridized. That's where the electrons are around an individual carbon. Molecular orbital theory says, well, that doesn't make much sense. When you start sharing electrons, the entire molecule becomes a thing. A weird example that maybe will work or not is, anybody in here seen Guardians of the Galaxy, first one? The second one was like, the third one I don't have high hopes for. But in Guardians of the Galaxy, in the first one, there are these stones called Infinity Stones. And if one person hangs onto a stone, you basically blow up. It's an ugly situation. And spoiler alert, if you've not seen Guardians of the Galaxy. At the end of Guardians of the Galaxy, main dude grabs a stone and he's like, I'm about to die. But then his friends hold his hand and they share the energy across all of them. So it's not just one dude hanging on to the Infinity Stone. It's this whole team hanging on to it. They spread out that energy among everybody. Those are how molecular orbitals work. When I make a bond, if I'm a carbon and you're a carbon and I go, hey, nice to meet you. It's not like I have my electrons and you have your electrons. We shake hands and we become a brand new thing, right? We turn into a molecule where the electrons aren't yours or mine. They are now ours. They act in concert together. So that inherently makes things a little more complicated, right? Because it's not just your electrons, my electrons. So, hey, I'm leaving with my electrons now, right? We have to talk about them in terms of a whole molecule. In order to make this not so crazy, and in order to not talk about Marvel movies, let's talk about hydrogen. A hydrogen is going to make a bond when one, let's put this on an energy scale. When one hydrogen molecule with a 1s orbital brings one electron, another hydrogen with its 1s orbital brings one electron. So these are atomic orbitals, right? I'm describing an H atom with one electron, an H atom with one electron. When they come together, they're going to drop down in energy. I've drawn a picture for you like this before. I just didn't call it a molecular orbital. This makes an H2 molecule, also known as a what kind of bond? Sigma bond. A sigma bond is actually a molecular orbital. When one hydrogen binds to another hydrogen, it doesn't make there's not like an electron floating over here and an electron floating over here. They just turn into a soup of the bond between the two hydrogen atoms that we call a sigma bond or a molecular orbital. That's where we get bond strength from. How far this drops is how strong the bond is. The part that gets really funny about molecular orbitals is that energy can go down. The energy can also go up. This is a theoretical space that for hydrogen is not occupied, but is referred to as a sigma star or an antibond. Do I regret putting this down here and not starting a new page? Yes, I do. Is this going to be a theme? Probably. Again, I used to teach this on the board, so sorry about squishing everything down here. When two hydrogens come together, the electrons can fall down into a safe, happy place. If I put any more electrons in this system, they're going to go up in energy. Remember, when you go higher in energy, that is a destabilizing force. If I took an H2 molecule and I shot it with an electron gun, the H2 molecule would not like that because the electron would have to go into this anti-bonding orbital. This is a theoretical place that is empty until electrons start to occupy it. And this normally drives students crazy because they're like, why are you even showing me this thing that's not real? Because we can use it to determine if a molecule forms or not. So I think the best way of showing that is, let's talk about not hydrogen, but an atom that has one more electron in it, which is helium. So He, 2. If I do this same treatment with helium, I would have a 1s orbital on this side and a 1s orbital on this side. That is a helium atom, 1s, helium atom, 1s. Those are individual atoms. How many electrons go in this 1s orbital? Deuces, right? Periodic table tells us that there are 2 electrons around helium, not just 1. 2 electrons here, 2 electrons here. A helium runs into another helium atom. We're going to drop down in energy and form a helium-helium sigma bond. Is that the only molecular orbital that I'm going to form? Because I've got 4 electrons that I'm trying to interact here. So 2 went down, but 2 also went up. That means my sigma bond and my sigma star bond are both occupied. Do heliums form a bond? No. This is why. When a helium tries to share electron density with another helium, it is as beneficial as it is destructive. So they go up and go, hey, nice to, never mind, we're good. And for that reason, if I had 2 tanks of gas up here in front of me, a hydrogen tank and a helium tank, if I opened the hydrogen tank, hydrogen molecule would pour out, H2 as a molecule. If I open my helium tank, my voice would go up, right, and I'd float away, and helium atoms would come out, not He2. This does not exist. Because molecular orbital theory tells us helium's making a bond is as helpful as it is hurtful, so they'd rather just be atoms. There is some really, really complicated physical chemistry behind it about wave formation. So if you want to learn more about it, I can talk to you offline, but it's about constructive and destructive interference. Waves add and waves can destruct one another. But as far as we're concerned, when you have 2 electrons in a bonding interaction, that's a good thing. When you have 4 electrons in a bonding interaction, it's a bad thing. And we can use this theory to predict if a molecule is going to form or not. That make sense? Ish? Kind of? Does it make enough sense? Okay, there is a whole class called physical organic chemistry about this concept. The reason I bring it up is we'll use a lot more molecular orbital theory in OChem 2, but I want you to be familiar with, I am somewhat lying to you when I'm like saying, oh, you have an electron, I have an electron, we shake hands, that's a bond. Easy, right? There's a lot more complex theory that goes on top of that. We'll leave that alone for now, because the last thing I need to show you in chapter 1 is I need to make you better at drawing chemical structures. So let's take a break from all this theory and go back to picture time. Okay, I want everybody to put their pencils down and time me. I'm going to draw a molecule for you. It's going to be 6 carbons in a chain. We're going to put an OH on the outside of it. There we go. Boom. This molecule is called phenol. How long did that take me? 11 seconds. I want you guys to draw phenol. On your mark. Get set. My timer. I'll just do it in my head. Go. When you're done, put your pencil down. No, I can't take a picture of it. You gotta draw it. "25 seconds, 28 seconds, 30 seconds, 30 seconds. "45. Click. 50 seconds. About there, right? So about a minute for the longest, about 25 seconds for the shortest. We're going to draw some really complicated structures. If I have to draw every molecule in this class like this, it's going to take us forever. So I'm going to redraw phenol for you in a way that is much more palatable. That is also phenol. Everybody draw that. Go. Seconds. 11, 12, you get the idea, right? Much faster. I know you're having to like look back and forth, make sure you get all your notes just right here, but this is called a skeletal structure. What's this called? This is called line, or the other name is keculae. We need to learn how to draw molecules as skeletal structures. I don't know why I drew this so freaking huge, but I'll put it in over here. I think this will fit. So we got some rules for skeletal structures. Rule number 1. Notice what I didn't draw in here. Carbon. That's kind of weird, right? This is organic chemistry. We're obsessed with carbon. Why didn't I draw it? There's so many of them, and every molecule we're going to draw, they're just everywhere, right? We're inundated in them. So carbon atoms are not shown. They are assumed. They appear at the ends of lines angles and intersections. So let's look at the molecule over here. How many total carbons in phenol? 6. That is represented in my skeletal structure by 6 angles. 1, 2, 3, 4, 5, 6. Where there's a bend, there's a carbon atom. Rule 2, hydrogen atoms are also not shown. Carbon and hydrogen are best friends. Everywhere there's a carbon, there's probably a couple hydrogens on there, so we don't show them. If they're bound to carbon. You need to mentally supply enough to give carbon an octet. If there's a charge shown, then you account for that with your hydrogens as well. But we're not going to work in charge structures just yet because you don't know how to count charge. So there's a carbon at this bend. Actually, this one's the breakthrough. Let's go to this one. There's a carbon at this bend, right? How many electrons do I have shown explicitly for this carbon? 6. 2, 4, 6. That carbon must have an octet, so I know that there's a hydrogen there. I don't draw it, but I know there's one there because my skeletal structure allows for me to have hydrogens that make up an octet for that molecule. This carbon has 2, 4, 6. There must be a hydrogen present. How many hydrogens on this carbon? None, because that carbon has 2, 4, 6, 8 electrons shown. So I don't add any hydrogens there. It would break the octet rule. I use hydrogens just to make up the octet rule. So I know there's one here. Don't draw these, but in blue, I know they all have to be there to give each one of those carbons an octet. I have another example for us. So I know we probably need to hit on that a little bit more, but we'll come back to it. We're going to show all non-carbon atoms. And this is not an official rule, but something I want you to do. I want you to draw in the lone pairs while you're learning. I put an exclamation point because I feel strongly about that. Draw in your lone pairs. They don't have to be shown in a skeletal formula, but it is going to make your life as an undergraduate organic chemistry student much easier if you put the dots in there. I got 3 minutes. Let's do an example. I got to clear this screen. Is that okay? So I have to draw the hydrogen on this nitrogen because a skeletal structure must include all non-carbon atoms with hydrogens. I'll put my lone pair there. I want you to tell me about the hydrogens that are in this molecule. Are there any on this carbon? On this carbon? Yeah, how many? 1. Any over here? Yeah? 1. 1. 1. It's getting boring, huh? 1. Here? None. This carbon has 2, 4, 6, 8 electrons, no hydrogens. Any here? 2. Any here? 1. Any down here? 3. That is a carbon. The end of a line counts as a carbon, so there are 3 hydrogens down here. I don't need to put any over here, right? 2, 4, 6, 8 over here, and 3 right there. Everything in blue is what I'm filling in mentally. I wouldn't show that in a skeletal structure. If you need to draw them out while you're learning skeletal structures, that's a great technique, and then remove them later on when you're trying to do this on your own. Everybody see how I filled those in? Okay, this group on the end here is a CH3. When a CH3 is attached to something, it is called a methyl group. The rest of this molecule, without all of that, is a common name of a molecule called amphetamine. Amphetamine is the active ingredient in a lot of different things. It's used in a racemic mixture for Ritalin. Okay. If you put a methyl group on the end of amphetamine, you have made methylamphetamine or methamphetamine or just meth as we know it. I do not endorse drug use in here, but methamphetamine is very much an organic target, and we will talk a lot about the structure, properties, and how to make meth later on in class. But for now, we'll just worry about the skeletal structure of it. We'll start off with chapter 2 on Wednesday. I look forward to seeing you then. Oh, we have an action center starting like in 10 minutes. So if you want to practice some of this stuff, feel free to meet me in the science building, room 248. It's on, the other one is on Wednesday from 10 to 10:50, just before class.